you to our, and I'm going to say it again, our Leiden-Delft-Erasmus Center for Sustainability Circular Industries talks. It's a long thing, but of course, most of you will know that we have this Leiden-Delft-Erasmus collaboration on all kinds of topics. One of them is, for example, the medical delta, but we also have the Center for Sustainability, and within that, we have the Circular Industries Hub, in which we're looking at materials, resources, circularity, recycling, all things related to kind of creating a more circular industry. And we have been focusing a lot actually on metals and metal recycling, and metals are of course very important for the energy transition in terms of batteries and electromotors and steel for the turbines, etc., etc. But of course, one other very interesting type of material, group of materials is composites. And or composites, I'm not sure what you say, but you will correct me later on, Jelle. And therefore we asked Jelle Joustra to come to our Circular Industries talks. He is a postdoc currently at the Circular Product Design Department of TU Delft, and he is also the academic coordinator of the Leiden-Delft-Erasmus Center for Sustainability Circular Aerospace Thesis Lab. We have these thesis labs in which students work together on a specific topic. So we have one on hospitals and recycling in hospitals, etc., and materials in hospitals, and we also have one on circular aerospace. So you will be presenting, Jelle, your research, which resulted in a publication and a design guide, Circular Composites, a design guide for products containing composite materials in a circular economy. A very challenging topic because I think it's probably a lot harder to make it circular than, let's say, metals, which you can just remelt and then you have the same material again. Probably a bit more complex for composites, but I'm happy to hear more about it. So Jelle, with that, the floor is yours.
Thank you. Indeed, in this talk, I'll present you the result of my research in the past few years. Coming Monday, I'll also defend my thesis on this topic. So it's a great moment also to present on these outcomes. So I've been looking into composite materials for being used in products for a circular economy. To start, what are composite materials? Generally speaking, it's a combination of fibers in some kind of orientation and a matrix material. And with a matrix, we mean a thermoset or a thermoplastic resin, which embeds those fibers. And those fibers can be long, short, oriented in unidirectional order, or crisscross mingled together. And all these variations in materials which you can use and their alignment makes for very tailorable material properties, which means you can really optimize or specify the type of material for your specific use case. We mostly know them for their high specific stiffness and strength, so very strong and stiff materials versus a very relatively low weight, which makes for lightweight and thereby fuel efficient applications in transport or very large structures. Some examples. For example, on the bottom left, a very fuel efficient racing car made with carbon composites, made for a very light bodywork, a very light structure, which effectively reduces the weight that has to be carried around. That was a prototype, but it's also used a lot nowadays in mass production. For example, most of the cars we see around us now have variations of composite materials used in their dashboards, fenders, and all kinds of underbody components. Also, aviation is a very large industry using composites because, well, obviously the weight reduction, and we see, well, the percentage of composite materials being used in typical aircraft increasing year by year. Another one, already highlighted were wind turbine blades. And there we see another property which comes in to good use. It's their relatively high stiffness and strength, which means you can make longer and stronger blades, which will effectively increase the power generated per wind turbine. While these materials offer obvious advantages in use, their end of use is less poetic, because at the moment the recycling capabilities for composites are just very limited. You'd have to try to separate the fibers from the matrix, which usually is a very tough chemical or thermal process or a combination of those. And those processes, reduce the material properties. They're very cumbersome and don't just really deliver. So at the moment, we unfortunately see that a lot of these materials are simply dumped at the end of life. This is a landfill site in America, where they're really just burying these spent wind turbine blades. Obviously, this is not a solution that we're looking for. To prevent these things from happening, we really have to look into the design of composite products, which means that throughout the complete design process, we have to pay attention to what's going to happen at the end of the use stage. So already in the concept development, embodiment, detail design, and preparation for production, we have to think about what's going to happen next, what's going to happen in the recovery stage, and anticipate. So think ahead, what will be the recovery pathway look like, and how can we adapt the product to ensure that it's really feasible to recover it as such. When my research started, we didn't really have a lot of pointers as to how to address this already in the design stage. So what we did was start mapping a product value chain, because evidently it was very important to consider what happens in all stages of a product production and its use, and to find out in which ways we could alter those processes to make sure that we can keep using the products for longer, or to recycle them effectively. What we did is I was embedded in a Horizon 2020 project, EcoBulk, and within this was a large consortium of about 30 partners from industry and academia, and we started mapping out the value chain for a couple of case products and identifying recovery strategies and how these could be facilitated by design. This delivered a number of strategies to break from our current perspective. I've laid them out on a value hill. So what you see here is a typical product life cycle as it is right now, where we start out with materials at the bottom left, which are produced into components, assembled into parts, installed on site and used for some time. And after some use phase, at the moment we see this sudden drop in value, which is when they're dumped. What we need to do is to extend the product lifetime, to make sure the product keeps being in use for longer, enable lifetime extension, product recovery, structural reuse, and recycling. And these are all strategies to reconnect the latter part of the product life cycle with the starting part. So to make sure that these materials and these parts keep existing within the economy rather than floating out of it or being dumped or demolished. We also found a number of design aspects. So how can we enable these recovery strategies in the design? These are interventions like ensuring adaptability, selecting the right type of materials, implementing standardization of parts, designing for dis and reassembly, developing connection solutions which really match the type of recovery that you intend to do. And within this cloud of design aspects, we started finding clusters. So we saw that these were interconnected and as such formed groups of design aspects to implement on your product development. But within these explorations and the work we did within the large project, we didn't really find the strategy of structural reuse. And structural reuse is a very interesting opportunity for composite materials, because what we intend to do is, rather than, well, recycle a material, which usually starts with shredding it to smaller bits and then trying to reprocess it with thermal or chemical processes, we're aiming to reuse parts of a structure as is. So by either repurposing, and this is an example project we did, developing a bridge out of wind turbine blades. And what you see here is that you can really effectively use a part of the functionality of this initial product in another use cycle. So in this case, we used 2 wind turbine blades as load-carrying beams for a slow traffic bridge. This requires relatively little processing effort and extends the functional lifetime of the blade with another 20-30 years. But the drawback of this approach is, however, that it's it can be pretty occasional. So while you can build a lot of bridges, for each bridge you would have to, well, figure out what type of blades are available, what type of spans do we need to cross, and this may limit the series production or the mass production which we need to accommodate for the large volume of materials that is coming at us. So another approach was segmenting. There we'd segment large structures like these blades into standardized panels and beams, which can then subsequently be used in all kinds of applications. Because, well, a large unit, like a large single piece, like a wind turbine blade, is very hard to fit in a secondary use cycle, while standardized panels and beams, well, there's so much opportunities for those. There's so much things being made with standardized building materials. This picnic table was one exploration which I did, where I took part from the wind turbine blade, reprocessed them or cut them to size, and then used them to build this table. And I also looked into a more serial approach on this. So if we have a wind turbine blade and we know its general dimensions, can we define a good segmentation pattern which will deliver useful components? For this, it's good to know that a wind turbine blade as is not just a solid block, so to say, but it's actually consists of various parts in itself. So in light yellow, we have pretty much lightweight materials. They have a core of foam or balsa wood, and they have glass fiber reinforced faces. Then in orange, we have solid glass fiber materials or even carbon fibers. And in blue, those are also pretty light foam-filled stringers. So there's already different types of materials to be harvested and also different shapes to be harvested. And I found that if you take the curvature of the blade into account and consider that it's a blade of 60 or 80 meters or even more, that it's very well possible to extract construction materials which are still within the conventional building standards. So you'd have panels, instead of plywood panels, you'd have fiber reinforced panels. And these panels, they're very strong, they're very light, thereby I think they're very valuable. From these explorations, I elicited a number of design insights. So what can we do in the development of new wind turbine blades or other composite structures to ensure that they're suitable for structural reuse as is. And those are insights like using monitoring over the product lifetime to ensure we can accurately establish the material quality when it comes in. But it also means that we need to have the identification of the blade available and documentation on its shapes and material composition to ensure that we can find high value and proper applications for the secondary materials. All these insights from the case studies in EcoBulk and my own explorations on recovering wind turbine blades came together in the Circular Composites design method, which starts with the situation as is, and then by mapping out the value chain, as I've shown before, and finding the right design aspects to implement on your product, you'll find opportunities for reuse and recovery of your composite product. And all these insights were brought together in a framework. So here's a framework that connects the 5 strategies: long life, lifetime extension, product recovery, structural reuse, and recycling, to those design aspects. And this will help designers to figure out, if I'm aiming to develop my product for lifetime extension, which type of interventions can I make to my design? Or if I'm looking for long lifetime or for recycling, how to adapt the design in a way that it's more suitable for those recovery processes. And this design method was in the end tested in 5 case studies with EcoBulk. So we had a pavilion built of plastic composites. We had a set of bedroom furniture and 3 cases in automotive industries. They developed various types of dashboard components. And we supplied them with the information on this circular design method, and they used it in developing their new prototypes. And by analyzing these cases on how they implemented the design aspects, we found that the design method was actually found to be very accessible, so easy to understand and use. It was very usable. And to a certain extent also effective. Why to a certain extent? Well, even within the scope of a nice Horizon 2020 project, we found that there's still some considerations on the industries, the industrial context in which they operate and their business models, which limit developing a fully circular product proposal. But within those boundary conditions, we were still able to make some steps towards a more circular product in automotive industry and also in construction and furniture. And everything was then brought together in the Circular Composites design guide. And the design guide is really a really accessible way of bringing the circular composites design method to industry and also to academia, to everyone that's interested, basically. It shows all the things that I've just shown before and more. For example, for every one of those design aspects, we list some descriptions, examples from the cases we've done, and there's a couple of design guidelines to take into account. So it's a very accessible and a nice book. And you can download it as a PDF, or you can get your own copy by print on demand from the TU Delft Open Publishing. By that, I want to end my slideshow for today, and I'm open for some questions from the audience.
Thank you, Jelle. And I'll give a real hand that you can hear, and I see also some virtual hands coming along. So thanks for your presentation, and thank you for taking us in the interesting world of composites and composites recycling, and showing us, well, that there's a lot more possible than I at least thought would be possible. So the floor is open for questions, of course. I don't see any hands raised at the moment. It always takes a bit of time for people to digest, so I'll start with asking a question myself, maybe. So I think it's very interesting because I think metals are so different from these types of materials, right? I mean, metals are just, yeah, you can get exactly the same or even higher quality metal out of recycled materials if you like, and if you process it right. And here, if you are, and I really see how you can use if you slice up, let's say, a wind turbine blade in different standardized parts, then of course you can use that in standardized production of all kinds of products. And I'm just wondering, I think that one of the things that the people that really like cradle to cradle, they would argue that you should never use a material that is not biodegradable by itself. Now, of course, wind turbine blades with glass fiber and epoxy resins are not biodegradable by itself, and still, well, in certain cases, you really need this type of material. So, and just as a devil's advocate, so once you're slicing up wind turbine blades in small parts and you're making smaller products out of it, then at the end of life of that product, you will end up with waste from that product, and you might slice it up in different pieces, or you might end up with the standardized modules that you can reuse again directly, maybe in other products. But in the end, you will end up with waste, right? And it might be smaller and smaller waste, and it might also not be that identifiable, let's say, as wind turbine blades, which are large, you know where they are, you know where and now it ends up in society somewhere, and it ends up in regular waste, and it ends up in regular waste incineration plants, because that's where furniture often ends up. So how do what's your view on that? I'm just wondering.
Yes, well, considering the cradle to cradle perspective, well, stuff has to be biodegradable by itself. Well, I think we can also, there's also a lot of materials which you can use which are very well processable by technology, so not by nature immediately, but we do have the technology to reprocess them and reuse them, which makes them suitable to use in a circular system. Composites, however, they're more of a persistent nature. They will degrade, but only very slowly and in a way which, well, doesn't really deliver nutrients for nature, so to say. So what we need is proper reprocessing technology, or a combination of a material and an appropriate reprocessing technology. At the moment, we're not there yet. There have been some alarming reports, for example, by the German Ministry for the Environment, saying that, well, our reprocessing capacity is not up to speed, and it won't be for the next couple of decades. So I see my approach of structural reuse, not really as a, well, an end solution, so to say, but more as a, well, prolonging product lifetime solution. So we can extend the value and the time, and we can extend the value over time, actually, of these materials. And we store the materials in use rather than somewhere underground. And what I hope is that then, well, within the time that we keep the materials in use, well, a typical bridge can last easily for 20 or 30 years. That by the time then we will have hopefully more reprocessing capacity and more opportunities for valuable reuse. Yeah. Oh, you're muted, René.
The most used phrase nowadays. You are muted. Thanks. So I understand your answer, and thanks for that. But I'm still wondering about, well, if you are distributing, I mean, a wind turbine blade, if it's a complex material and it's complex for recycling and reuse and even waste processing and anything. Once you have wind turbine blades, you know exactly where they are and how to process, and you can get them out and have a separate processing facility for it. Once you have furniture, it's out there, right? I mean, it just goes into the regular waste, and you're not going to collect it separately or something like that. It just goes into regular waste, and it will be an issue maybe for waste recyclers. So what's your view on that? So shouldn't we do that? Shouldn't we make those types of products, or should we only make, let's say, the larger ones like the bridges, etc.? Or do you think that we should also be using this material for these more consumer-based products?
Well, there's a question of traceability and control over the product life cycle there. And typically within business-to-business environments, and especially large volumes, well, a wind turbine blade is a large integrated volume of a specific type of material. They also come in sets of 3, and usually in wind farms, multiple sets of 3. So that's very traceable, very controlled. Indeed, if you start cutting up those blades, you have, well, a more dispersed volume. And then again, we need to, well, find ways for the traceability and control over those product life cycles, which may be in more business-to-business applications, or applications which are more interesting in terms of volumes. So one application area I see was also prefab construction. So there, within a single building, you could use various types of prefabricated components, prefabricated from a blade. You could have wall paneling, ceilings, load-carrying structures, which then again will, well, keep the materials pretty much in one place. And also, well, there's much talk about material passports and the likes, building information management, which will then keep, well, the materials traceable.
Yeah, so you would say don't use it for consumer products that go into regular waste, but keep it traceable. Use it in, let's say, larger scale business to business like applications, and you can still, once you have developed your specific recycling or waste treatment options, you can still trace it back to that and find it. Right?
Well, I'm not per se objecting consumer products. I think business to business is generally easier considering traceability. But also within EcoBulk, we had a partner working on identifications of composite materials. So if then the materials would end up in the general waste stream, and you'd have the proper, well, identification measures, there's infrared scanning or other types of scanning which can then, well, selectively divert streams of materials, then it won't be such a problem if it ends up in a general waste stream, if it's then diverted to the appropriate process.
If it is implemented in the general waste treatment system.
There we go. Yes.
Yeah.
Because, well, there's a lot of bad consequences from directly burning these types of materials in general waste facilities. It's pretty much undesirable.
Yeah, thanks. I also see a question in the chat, and that's basically how many times can the wind turbine blades be recycled? How many loops?
Well, that depends on the type of reuse and the type of loads and use scenarios it's exposed to. For well, the examples I've showed, we estimated that we can effectively prolong the blade lifetime with another 50 years. So we have 25 years in its original use. That's the design lifetime of a typical wind turbine. Then we can use it in a bridge. Bridges, well, slow traffic bridges are abundant around here. And you could use it in that way for another, well, 30 years or so. And then, well, after the bridge is disassembled, you could use this sectioning procedure to deliver construction materials and use those in buildings or warehousing, which could easily last another 20 years. And then, well, subsequently, you could add more and more use cases and eventually a recycling procedure. So, well, depending on the loads and the degradation it is exposed to, I'd say easily 50 years as a functional materials, and maybe even longer if we start, well, mixing it in with, well, more fresh or more virgin materials.
Maybe related to that, so we know that the market for wind turbine blades is growing quite rapidly, and we will have many more of them. And one of the things that I've seen is, for example, super use studios, which of course make playgrounds out of wind turbine blades. And then the question almost always pops up when I show that picture is, well, how many playgrounds can we make? I mean, we could basically use it for, well, there's enough materials for more playgrounds than that we need. And how would you see that? Let's say that did you also make some kind of projections about how much of this material will be available in the future, and how much could find a second life in some other application?
Well, the volume of end-of-use wind turbine blades is growing very fast. And that really has to do with the growth this industry has seen in the last decade. So blades with a life or with an age of about 20 years, they're coming back now. But this number is going to, well, multiply very fast. From our exploration into the bridge, into bridges, we estimated that it's actually a very feasible way of reusing them because of, well, the number of bridges, of these smaller traffic bridges which are built every year in the Netherlands. It would easily absorb, well, the annual volumes at the moment. However, at a certain moment, well, the supply of these blades will outweigh the number of bridges that we can build, or other applications, perhaps. So that's why I also was looking into, well, more diverse cases, more diverse ways to reuse these materials. But I think it's a constant, well, negotiation or discussion back and forth between what the supply of these materials is, what we can do with them, and by all means try to prevent dumping or combusting them.
Yes, thanks. Maybe I don't see any hands raised, so maybe a final question from my side is that you could also think, well, actually we shouldn't use these glass fiber epoxy resin composites in the future. We should go and the project that you just mentioned that you just started is also looking at more bio-based or other materials. So do you think that in, let's say, 10, 15 years from now, we will still be using epoxy resin glass fiber turbine blades, or do you think we will have something completely different available then?
We will have something completely different available then, but I do think that we'll still see glass fiber epoxy in use. There are a lot of promising material developments going on and associated reprocessing technologies. They're them being bio-based or thermoplastic resins. Thermoplastics can be remolded after use, just like metals in a way, or even just shaped, thermoformed. And there's even thermosets, which are then reprocessable as thermoplastics or dissolvable thermosets. Well, there are all kinds of material developments at the moment, which are usually still at a smaller scale. And they're slowly climbing up, well, this technological readiness level ladder. But the thing is that, well, the conventional composite materials as we know them right now, they've had already, well, various decades of development and optimization behind them. So to get up to that level with the new materials, well, requires effort and time, and then at a competitive cost. So I think in, well, an overseeable amount of time, the technology will be available, and that also these new materials will be up to par. But then it's up to industry and market to also absorb them and ensure that they'll find their way into a circular economy.
And maybe also policymakers can come in to have certain standards for these blades. Of course, that might also help, right?
Yes. There's much talk about it.
Yeah. I think circular turbine blades. I think it's a big topic also on the political agenda now. Indeed, like you say, and yeah, it's interesting. It's interesting to see where that actually goes. I would like to thank you, Jelle, for enlightening us and taking us with you in the world of composites. I think it's very interesting for me at least. I really like the approach of creating standardized modules out of larger units that can then be used in all kinds of applications. So I think that really helped me thinking about these types of topics. So thanks again for joining us in our talks. Of course, it's also, as you know, this is also recorded, so people can also have a look at this afterwards. Yeah, thanks for joining us.
Thank you for having me. It was a pleasure.
Okay. Bye-bye.